Okay, hello everyone. My name is Mihir, and I'll be talking about Hall effects. So I'll be talking about various Hall effects, and then I'll focus in on one Hall effect and talk about its applications. So the common Hall effects I found in literature were the spin Hall effect and the anomalous Hall effect, and I'll also quickly review the classical Hall effect. So for the classical Hall effect, you can imagine you have a slab with current flowing through it, and if you have a perpendicular magnetic field, the charges will deflect and accumulate on the sides. So the deflection of those charges is what's really the Hall effect. And in this case, you'll get a Hall voltage, and this is related to a Hall coefficient, which is useful for telling you the resistance of the material. And in semiconductors, the Hall coefficient can also tell you if a material is p-type or n-type based on its sign. So in the quantum Hall effect, the magnetic field will cause cyclotron orbits. And in the middle of the material, all the orbits will be closed. But on the edges, you'll get skipping orbits, and these will cause edge states. So, and because of this, this is also called a topological insulator. And the reason why it's quantum is because the energies of the electrons get quantized into these Landau levels. And the amount of Landau levels that are filled will tell you the Hall resistance of the material. So I'll briefly cover the spin Hall effect because we didn't cover about this, and there's also the supplemental material in lecture 17, I think. So this occurs in materials with strong spin orbit coupling, and it doesn't need an external magnetic field. And the key feature of this is it converts electric current into spin current. There's also the inverse spin Hall effect, which converts current into, spin current into current. And these two conversions are key features used to make different devices. So the quantum spin Hall effect is similar to the regular spin Hall effect, but now based on the direction you travel along the edge, you'll get different spin states. And this is also a topological insulator. So for the anomalous Hall effect, this occurs in ferromagnetic materials. So when you'll get a Hall current, and the portion of the Hall current that's related to the coupling between the charge carriers and the internal magnetization is the anomalous Hall effect. And the Hall current you get is the dissipationless because when you get current that's deflected, it's not in the same direction as the E field. So if you use that relation E dot J to get power, you won't have any power. So similar to the spin Hall effect, this can also exist without a magnetic field. And one feature of this is ferromagnetic materials have a higher Hall resistance than non-ferromagnetic materials. So in the quantum anomalous Hall effect, it's also similar to the other three, but now all your edge states have the same spin. So this is a topological insulator because the bulk is insulating, but the edges are not because you have all those edge states. And one thing you have to consider with this is you need Kelvin temperatures because you're using ferromagnetic materials, so you need to be under the critical temperature. But one advantage is you don't need a strong magnet to see the Hall effect. So one interesting emerging Hall effect is the anti-ferromagnetic quantum anomalous Hall effect. So the key thing here is with the ferromagnetic metals, you have to stay under that critical temperature, and it would be nice to use insulators which have a much higher critical temperature, and you can operate them at room temperature, so you won't need cryogenic coolers. So if you have collinear anti-ferromagnetic insulators, you can achieve the quantum anomalous Hall effect much more cheaper. And like we talked about on Monday, this will give you ultramagnetism. So these two figures here, this first one shows you the band energy diagram of the collinear anti-ferromagnetic materials, and this diagram here is a Berry curve. So the Berry curves, they're related to the geometry of the material, and they're also closely related to the spin Hall effect. So a lot of the work revolves around like trying to change the Berry curves to get different features. So next I'll be talking about the nonlinear Hall effect. The nonlinear Hall effect I saw three main applications you can use it for. You can get these piezo-like strain effects. You can use it for memory, and the thing I'll be focusing on is using it for terahertz emission. So first I'll cover what the nonlinear Hall effect is, and then I'll discuss how you can use it for terahertz emission. So when you apply a voltage, you'll get two currents. One of them will be DC, and the other one will be an AC current at double the frequency of your input. And the linear and nonlinear terms depend on the symmetry of your device. And specifically, the second order term requires a broken inversion symmetry. So this is like if you rotate your material, you need to break that symmetry. And there's like different variations of this effect. You can drive it thermally or electrically, and you can get either electrical responses or non-electrical responses. So next I'll be talking about bismuth, which is a popular material which is used for this. So before like bismuth is commonly used, getting the nonlinear Hall effect requires really low temperatures and materials that are toxic to the environment. So it's not that practical to use. So bismuth has good spin orbit coupling and it's already used in topological materials, but it does have inversion symmetry. And to get the nonlinear Hall effect, you need to break that symmetry. So at the edges and the surface of the material, that symmetry will be broken. So you can still get the nonlinear Hall effect on the edges. And by engineering to exploit that, you can use bismuth to get the nonlinear Hall effect. So a lot of the things they do is create a bunch of arcs, which will help you get them. So like over here, these would be the different arcs, giving you different nonlinear responses. Oh, and the nonlinear response is usually a quadratic response between the applied voltage and the current you get out of it. So to get terahertz emission, you make a whole array of these small curved devices. And for this particular bismuth device, there's a center frequency at 0.3 terahertz, and you can also get second harmonic generation. I think even with this device, you can also get third harmonic generation. So it is good for terahertz emission. And then this terahertz emission can also be improved upon because one disadvantage with the bismuth is you only are getting spin conversion on the edge. So like a lot of material is being wasted. So they call that a low spin to charge conversion. So there's actually another kind of terahertz emitter, which is based on spintronics. And that's using that feature of the spin Hall effect when you're converting between the two currents. So if you increase your spin Hall angle and increase interface scattering, you can improve the terahertz emission. So the main way they increase the spin Hall angle is by adding impurities or using alloys. So the conclusions are there are different various Hall effects, and sometimes you want to consider their properties. Maybe it's a effect that you don't want, but you can also exploit that property to create a device. You can also use topological engineering to exploit the properties of certain materials to make them used in situations where they aren't normally used. And if you combine these two things, you can get many cool devices like terahertz emitters. And these are my references.